Good morning, everyone. Today we will continue solving circuits, applying Kirchhoff's rules on those circuits. And in the upcoming two lectures, we will talk about the RC circuits. So we have this circuit that we need to find the VAB. Remember, we talked about the double indices, that the first one represents the higher potential and the second one represents the lower potential. So here we have VAB. We want to solve for VAB applying Kirchhoff's rules. So in this case, let's draw the circuit. So we have here 12 volts, 1 ohm, A, B, 1 ohm, 3 ohm, 2 ohm, 8 volts, 1 ohm, and 2 ohm. And this is my VAB. A is higher in the potential than B. So how do we solve this problem? Okay, so it is very important to notice here that this circuit is open because I have a broken circuit here at A and B. What does this mean? This means that the current going in this branch is 0. This is extremely important. So if I'm now to apply Kirchhoff's rules here, let's assume that my current here, now since this one is open, I have my current here. I'll call this one I. And now this current is the same going all the way, right? Because it is one loop only. So the current has to go in the same direction. So this is I. Now, if I assume this one I1, just for the sake of writing the KVL equations, and it is 0, then if I take, for example, this loop as L1 and let's see, and this one as L2, and then I write the KVL here. Okay, so let's start first with loop number 2, because in loop number 2 I have only one variable, which is the I. So I will say KVL at L2, and in this case I have L2 going in the same direction as I, which means the resistors here will be written as minus. So I have here start with from here. I have minus I, then here minus 2I, minus 2I, minus I, minus 8 because I am entering the positive terminal, then minus 2I, minus I, plus 12 equals to 0. So this is my KVL equation for loop number 2. And here I have, let's add this minus 1, minus 3, minus 5, minus 6, minus 8, minus 9, minus 9, I equals 2, minus 8 plus 12 is plus 4, 0, and then I have I equals to 4 divided by 9, or I equals to 0.444 ampere. So this is the current. I got the current from the bigger loop because I only have one variable. Now I can make use of this I and find the VAB in loop number 1. So in this case, I would say KVL at L1. Let's write KVL for loop number 1. So I have L1 going clockwise, and it's anti-parallel to I, which means it will be written for the resistors. It will be written as positive. So let me start from the same resistor. So I have I minus 12 plus I. Then I'm now at this resistor where I1 is parallel, and that's why I'm writing it as minus 3I1. However, I1 is 0, plus 10 volt because it's entering the negative. Again, minus I1, also 0, which is this resistor. And then entering the VAB from minus, so plus VAB, and then the last one is this. It would be again plus 2I equals to 0. So what do we have here? We have I, 2I, 4I, we have VAB here, 4I, and then we have minus 12 minus 2 equals to 0. Then VAB equals to 2 minus 4I. VAB is 2 minus 4 times 0.444. Then VAB equals 2.22 volts. The second question here, we will be solving it by inspection. So the question here is asking if all those resistors RA, RB, RC, RD, and RE are equal. What is the current in the resistor RC? Now, by inspection, and because all those resistors are equal, then the potential at B at this junction equals to the potential at this junction. So I have here VB equals to VC. So if the potential is the same due to the symmetry, then VB minus VC is 0. And if this resistor RC has a potential difference across that is 0, then definitely the current entering into this resistor would also be 0.